All right, so now that we know something about relative age dating, hopefully you've looked through the PowerPoint on relative age dating in the video. And so we want to talk a little bit about absolute dating methods. So yes, the relative age dating principles are useful, but we'd like to know more. And we can because we now have the ability to analyze certain rocks and determine a numerical age. And we can add that to our repertoire, and that helps us figure out what we know about the history of the Earth and the timing of the history of the Earth. And so in order to do that, we need to remember just a little bit about atoms. Now, there is a section that we'll talk about this week on or not this week, but you'll talk about in the module on minerals. And we'll go through a little bit of the atoms and elements. So this is, a little intro, but we're going to focus more on what's called an isotope. But I'm sure you know what atoms are. They're the smallest piece of matter that exists that have unique properties. And you know the parts, I'm sure you remember. But if you don't, here they are, right? So what is an atom? It's composed of a nucleus. And within that nucleus, we have protons and neutrons. Proton is the positive charge. Electrons circle our nucleus, and those are negatively charged. So we might have seen this diagram in high school or whenever you learned about atoms. It kind of looks like a little solar system. In reality, there's these shells that hold the electrons, and they have different energy levels and all that kind of good stuff. We don't have to get into all that. We just want to kind of refresh your memory about how this works and explain to you that we have something called an isotope, and that is something that we're using to figure out how old these rock layers are. And so the other thing to remember when we talk about atoms is that the protons are telling you what you have. So if we look at a periodic table, there's atomic numbers, and those are related to the number of protons. Okay, so if you have 6 protons in your nucleus, you are a carbon atom. If you have 1, you're a hydrogen atom. If you have 92, you're a uranium atom, and you can't be anything else. That doesn't mean I can't mess with these other things, like neutrons, right? And so I can do a little bit of weirdness by changing a few other things in my atom, but I can't change my protons yet. And so if we look at this is our periodic table, you can see the numbers here. These are atomic numbers. But they also are going to refer to the number of protons, right? All oxygens have 8 protons. So if someone ever asks you on a quiz, hey, look here, sodium, that's 11. Okay, must have 11 protons. And that's all true. But we do find that we have things called isotopes. And isotopes can be things that have these extra neutrons in them. And so here I have a carbon atom, and it typically has 6 protons and 6 neutrons, but I can get some weird versions that have an extra neutron or 2. And these are what are called isotopes of our stable version. And a lot of times these isotopes are unstable, and so they change or they break down over time. And that's something that can be helpful to us as a clock to figure out how old our rocks are. Okay, and so what we see is that this rate of decay, now it's complicated, and we're going to make it super simple here in our introductory geology class. The idea is that some of these unstable isotopes will change over time, and the rate is what I'm going to call a half-life. And so it acts like a clock, and it kind of tells me over periods of time, and usually long periods of time, how long it would take for half of this unstable element to decay to a more stable element. And so we're going to use that idea to kind of figure out ages and numeric things, right? So a lot of these isotopes are available in certain rocks, but not all, okay? And so we have to be specific when we choose a rock to analyze. We can't just grab any rock willy-nilly. Now, the good news is that what we're going to find out is igneous rocks are really good at getting these age dates on. because of the way they're created, they're molten. And so these atoms are kind of moving around and they're not crystallized. And then as they cool and crystallize, they kind of lock in these elements to form these minerals that make up the rock. And when they're locked in, then the clock starts ticking. But I have to find, like I said, specific rocks, not just any random one. I have to find one that can fit in these bigger, unstable isotopes of a certain element, and not a stable version. So what we'll come to find out is that we need only the unstable version to be fit into my chemical formula to make my mineral. Because over time, that unstable element is going to change in place to a stable element. And so we sometimes use the terms, or we do use the terms, that there's a parent element and a daughter element. So the parent is what the unstable version starts out as, and over time, as the parent changes, decays, it changes to what we call a daughter product. And so we can see that there's parent and daughter in a rock that I might find today, but when I start off, I don't have any daughter product. And so how does that happen? Well, we basically can change some stuff. The radioactive, this unstable part, can decay in a bunch of ways. One is called alpha decay. This is where I kick out from my nucleus some protons and neutrons. So yes, in certain cases, I am changing from one element to something else. So you may have heard, or maybe not, but uranium to lead is a system that starts out with certain uranium isotopes that are unstable. They can't stay that way. They break down spontaneously over time, and they're going to change into lead eventually. That's the stable version. And we can figure out how long that can take based on what we talked about a little bit called a half-life. So now some other ways that you can change from the unstable to the stable is this alpha, but also beta, electron capture. I don't need you to know these types, but I need you to just be aware that there's multiple ways that we can take a unstable radioactive element, which we're going to call the parent, and we're going to convert it into a more stable version called the daughter. Now, when I mentioned this kind of changing from lead or from uranium to lead, this is the process that happens. So it's not a simple process. Like uranium doesn't just go poof and turn into lead. So it actually goes through this complicated process here of changing different elements until finally it makes it to lead, which is stable, and it can handle that. But here it is unstable in all these versions until it gets to here. And so we can look at the half-life between uranium and lead, the time it takes. It's a half-life is a time. Now it's a little weird because it's not like, 10. It doesn't take 10 years for one atom to do that because it's not easy to figure that out. But we can, over time, say, I can give you an estimate of how long it takes for half of what you started with in your rock to turn into a stable version. That's what a half-life is, right? And so if we were to look at something like this, we can make some very general observations. The idea that when my rock, and in this case we're saying that a lot of igneous rocks, so they're molten. When they cool and crystallize, they form minerals. The minerals are formed from these particular atoms. And in some cases, specific minerals can grab a radioactive isotope of an element and incorporate it in the structure of that mineral. So the good news about that is when I start at the very beginning, there's only these unstable isotopes that fit into this chemical formula that makes this mineral. And none of the daughter product is going to fit at the initial onset. And so it doesn't grab any of those, or there's none available, so it just grabs the unstable version. So at the very beginning, one of the big rules that we need to remember when we're figuring out absolute ages is that at formation, there are 0 daughter atoms in my mineral, and only there's parent. But over time, as time goes on, some of these unstable parents are going to convert into stable daughter product. And the longer my mineral has been around, the fewer parent and the more daughter. And hopefully that makes sense, right? As they're changing, and if it's fairly constant, then I'm going to see an accumulation of daughter and a reduction in parent. And so, we can look at something like this. Here's a magma, and I have these radioactive atoms and these stable atoms. In order to make a particular mineral, I need certain atoms to bond together. In this case, only the radioactive ones are included. Because of a size difference or a charge difference, that it's going to incorporate those into that mineral. So at that very beginning, when that mineral is first born, if you like, it has 0 daughter, 0 stable. Only the unstable exist. But then as it hangs around, those atoms are going to slowly change from the unstable parent to the stable daughter product, right? And so because the decay is nonlinear, it's this exponential decay, we use this half-life system. And so we can use that to tell us, how long and how many are left based on this system of exponential decay, right? And so we use the term half-life to figure out how old these rocks are. The idea is that I can estimate how long it takes for half of what I started with to decay. Okay, that's a half-life. The time it takes for half. So if my mineral contains, in the real life it would be millions and millions of atoms, but for simplicity, let's say there's 100 atoms. So in that mineral there's 100 unstable atoms. The time it takes for 50 of those to change from parent to daughter would be the half-life of this system. And now I have 50. In order to go from 50 to half of 50 to 25 would be the same time period, another half-life. And now I have 25. The time it takes for half of those to get to 12.5 would be the same half-life, the same time period. So we're taking half of what exists and changing it to the stable version. Okay, so some of these half-life systems are big. Uranium to lead is 4.5 billion years, right? Potassium to argon, 1.3 billion. Rubidium to strontium, 47 billion. Now, carbon to nitrogen is one that we use a lot of times for things that have carbon. So this is kind of the exception to the rule, is the carbon. These are on organics, bones and stuff like that. These up here are something we would use for rocks. And so, as an example, just to kind of get us on the same page here, because of what you know about how this system works, if I was to give you 2 rocks, a basalt, which is an igneous rock, and a rhyolite, which is another igneous rock, right? We would say if I counted in a mineral the number of atoms that are the unstable parent and the number of atoms that are stable daughter, and I got this ratio, this 5,000 to 5,000, and I have a rhyolite that has this ratio. Now we're going to assume that at the very beginning they had the exact same amount of atoms. You could tell me which is older, and that would be the rhyolite, because remember, the older the rock is, the less parent it has and the more daughter it has. Now this is of course a unique, weird setup where they started with the identical amount. So we would say that this rock B, the rhyolite, has been around longer because it's had more time for the parents to decay and to accumulate more daughter product, right? So as a word problem, or as in a problem that we would like you to figure out, what we do is something, where we would look at numbers and say, how many half-lives have occurred. And so remember, half-lives are this idea that it's time. So look, the rock forms. This is always, 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 always true. It has to be true for this to work. So what does that mean? Well, that means that if you're going to do this, you have to be a good field geologist. You have to be able to go out into the field and find the right rock, and then find the right minerals that are in that rock, so that you can confirm that that mineral does not include any of the stable daughter when it first forms. Then we can go ahead and analyze that. And that would be if we had 1,000 atoms, it forms, this is the ratio. And then after one half-life, whatever the half-life is of that system that we're using, this would be the count. After 2, after 3, and then we would just keep going. And so a lot of times the examples are, you're given, like, let's say 3 years, you're given this number, and you're being asked to say how many half-lives have happened. Well, the rule is, because this is 0 when it started, I just take the daughter and add it back to the parent, and now I know what I started with. Right? So an example would be something like this. A rock formed with 1,000 atoms, right? But only 250 parents are remaining today. So how old is the rock? Well, what do you know? Well, you know that this is what you counted when you went to your machine. You know what you started with. So you start here and you take half and you get 500 and 500. But that's not what you found today. But that would have taken one half-life. And in this example, the half-life is 100 million years. So it took 100 million years to go from 1,000 parents to 500. It took another 100 million years to go from 500 to 250. So 2 half-lives to get from where it started to where it is today. 2 times 100 million, this rock is 200 million years old. Okay? And so this could work in a variety of ways too. So we could also have one that we have where I'm giving you only this count. Maybe I only give you 250 to 750 and say, this is what you counted. Well, what's the age? Well, look, if you know these two, you know this. Any daughter product has to be parent at the very beginning. So if you're given this ratio, which this is typically what happens, right? I'm not told when I find a rock how many atoms were at the beginning. I'm told this value. My machine measures the unstable and stable elements and counts them for me. And if it gives me this count, 250 and 750, what do I know? I know at the very beginning there was 0 daughter. What does that mean? It means every one of these 750 was once a parent atom. And so that means that the starting point must have been 1,000. And then I just take half, until I get to the measured value, count how many half-lives, and multiply it by whatever the half-life is of that system. Okay, so there are some things that we have to be aware of, and that is we can't alter my parent-daughter ratio during the rock's lifetime. And so what can happen sometimes is that if heat or something weird happens to the rock, it can alter that. So we need what's called a closed system. Once again, this is why you have to be a good field geologist. You need to look at the rocks and know that they haven't been altered, because altered rocks would give us a weird time and not an accurate time, right? And so we can't have rocks that have been metamorphosed. That's why metamorphic rocks are really not good, because it can drive out some of the counts of the material. So that's going to throw off my whole count, and now I won't know the age of the rock. I might be able to figure out the age of the metamorphic event, but I wouldn't be able to know the age of the rock when it was first born, right? So remember, igneous rocks are the best. Metamorphic rocks are no good. You can do some said rocks if there's carbon rich. There's some bones or shells or things in there that have carbon that we could use. But igneous rocks, this is where all the glory is, right? Because of that crystallization process. Those minerals or those atoms that are floating around, we suck in those unstable ones and lock them into our mineral, and then they start to decay. So at that very beginning, we know there's no daughter in there, right? Let's see. We want to jump to that. So here's the conditions that we need, right? We need no daughter product at the very beginning. If that's true, we're good. We also need a closed system. We can't have it be metamorphosed or altered by water or anything like that. We need to have the rock as fresh as possible. And then, of course, we have to have a measurable amount of parent or daughter. If too many half-lives have gone by, then maybe there's not enough parent left that I can count accurately. Or if there wasn't enough of those unstable atoms to begin with, then of course that wouldn't be helpful. But what we can do with this information is we can use it to help us, right? So combining absolute and relative. And this is in the additional module, the additional resources page of the module. There's a second activity that I did and I do with the class where we kind of combine. So if you want to work through those, they can be helpful for figuring out some of this idea of absolute age dating. But although we sometimes can't date a rock because it doesn't have the right conditions, if I can date something above and below, then I can bracket it. So yeah, I don't know exactly what this layer is in the middle, but it's between 200 and 400,000 years. That's better than having no idea, right? So I know for sure lava flows, and now I can bracket this age. So we want to be able to do that. And in theory, that's how the whole geologic timescale was created. We started out with this relative story, and then as the numbers came in, we were able to kind of figure out and add it all together and come up with this very accurate geologic timescale that represents these rocks at certain ages, and of course, when these things occurred in the geologic past. So we can say, hey, 65 million years ago, there was an impact here because we can look at the rock record, and it can tell us all those cool stories. So once again, if we go back to our little cross-section here, now that I can say, look, these are igneous. This layer here, this layer here, right? These have some ages associated because they're igneous. Now I can still tell my story, but now I can tell an even better story. Before I could tell the order, but I had no idea. Did this sequence happen in 10 million years? Did it take 2 billion years for all this to accumulate? Well, because I know the age of the sill is 1.1 billion or 1,100 million, I know that A, B, C, and E all had to exist before that time. Those are old. They're 1.1 billion years old because that is this age here, right? So if I look here, it's telling me all those layers are older than, greater than that. Then, of course, I know the age of the intrusion itself, which is D. And then this came after, which was 900. And so, okay, so there's a 200 million year time period between this and this. But then, what about G? Well, I know this lava flow is 20, so it's older than 20. And this is the next thing I have, so it's actually between. I don't know what happened, but all I can bracket G, and remember, there's an unconformity here, an uplift, a tilt, an erosional event. I can bracket all that between 900 and 20 million. Tilting, uplift, weathering, erosion, and a positive G all happened within that time period. That's as best I can do, right? I know it's a big age gap, but that's what I know from that. But then I do know that these three layers have to be younger than 20 million. So that's a pretty good story now that I have both of these techniques, right? I have this relative and absolute combined together can tell us a really accurate story. And then when we learn about said rocks, we learn about, what type of environment existed here. There was an ocean here, 1 billion years ago, and then there was a desert, right? And then there was, a lake, right? So I could tell you when things happened and why they happened, and there was a plate boundary that caused a collision that uplifted these big mountains, and that's why these rocks are tilted. These are the stories we are able to tell because we understand these relative and absolute aging techniques. All right, so I think that's going to cover our story. Like I said, go to the additional resources and check out that second one that combines this absolute and relative, and it kind of talks about this if you need some more help with that. All right,